The Pauli's exclusion principle, one of the most important principle in quantum mechanics, I will discuss in this video lecture. But before that, some supporting physical concept which is required to explain the Pauli's exclusion principle. Number one is the quantum state. That means is space quantum state and spin quantum state. Space quantum state defined by these quantum numbers n, l, ml, a principal quantum number, orbital quantum number and magnetic quantum number, and with the help of spin quantum number, the spin quantum state. I have considered here only one eigenfunction, that is antisymmetric. There are two types. Number one is known as symmetric and number two antisymmetric eigenfunctions for the identical particles. And at number 3, Slater determinant is used if one have to write the antisymmetric eigenfunction or symmetric eigenfunctions for the identical particles. How I have used this supporting physical concept in this particular video lecture, I will discuss that systematically. So now the point is, according to the Pauli's exclusion principle, what he says that in a multi-electron atom, there can never be more than one electron in the same quantum state. Quantum state, my means here is again same, that means space quantum state and spin quantum state. So two electron cannot be exist in same quantum state. So Pauli exclusion principle specify the electrons properties only, not anything about the atoms. And this is one of the important concept in the Pauli exclusion principle, the waveform of antisymmetric eigenfunction. In the last lecture, I have told you about the symmetric and antisymmetric eigenfunction for two particles, and that form for the antisymmetric eigenfunction for the two particles is written as 1 upon square root 2, that is the normalization factor. Alpha and beta represent here the quantum state, and 1 and 2 these number for the particles. So for the two particles, identical particles, the waveform of the eigenfunction, that is known as antisymmetric eigenfunction. So this is equal to 1 upon square root 2 psi alpha 1 psi beta 2 with negative sign, and second combination is psi beta 1 psi alpha 2. Here we have interchanged the position of quantum state. Now for alpha is equal to beta, if these two particles are in same quantum state, this is the meaning of it. And for the two particles, let us see what will happen then. So psi a is equal to 1 upon square root 2 psi alpha 1, and here as you know that this label was for beta, now I'm writing it as alpha. So here there was beta, now I'm writing alpha. So now the result is psi alpha 1 psi alpha 2 minus psi alpha 1 psi alpha 2. So the result will be obvious, that will be equal to 0. It means psi a is equal to 0. The eigenfunction is identically equal to 0. So a system containing several electrons must be described by an antisymmetric total eigenfunction. This is one of the important point. And second thing, that two electrons, two particles cannot be in a same state with the same space and spin quantum number when we are using the quantum state word. The eigenfunctions we have been dealing with here obtained under the assumptions that there are two identical particles and the interaction between them can be neglected, right? So here we have assumed that there is no interaction between the particles. So if suppose we have to write the antisymmetric eigenfunction for more than two particles, then how one can write? So let us see that also, but before that, important statement that a system containing several electrons must be described by an antisymmetric total eigenfunctions, right? So now the problem is that determine the form of the normalized antisymmetric total eigenfunction for a system of three particles. Now particles are three and all the particles are identical, and we have to write normalized antisymmetric eigenfunctions. So as we know that for two particles the antisymmetric eigenfunction is 1 upon square root 2 psi alpha 1 psi beta 2 minus psi beta 1 psi alpha 2, and this form can be written as in terms of the latter determinant. Right, thus form of this latter determinant is for two particles 1 upon square root 2. If particles are 3 or 4, then we have to write here 1 accordingly. Right now there are only two particles, so I am writing here 2. If there are three particles, the example I will show you in the next slide will be 3 factorial 3. Right, so if there are n particles, then we can write here factorial n here and possible numbers into the determinant. So in the first row, if you see that the quantum state is defined by alpha in this way, and here particle 1, particle 2, and in the second row the state is defined by beta. You can see here this is quantum state with particle 1 with particle 2. So if I have to write the antisymmetric eigenfunction for two particles, then I will use this form of latter determinant. So here in this problem we have to write the antisymmetric total eigenfunction for three particles. So let us see. For three particles, one can write that in the first row you can see here alpha, alpha, alpha quantum state with these three particles 1, 2 and 3. In the second row you can see here that beta is the second quantum state, and here particles are in that is 1, 2, 3. Gamma is the third quantum state, and with that these are three particles 1, 2, 3. So here we will write, as I told you in earlier slide, that now there are three particles, so I will write here factorial 3. That means 3 to 1 that equal to 6. So 1 upon square root. And now how to write the eigenfunction? So we will basically expand this determinant with respect to first term, second term and third term. So with respect to the first one, psi alpha 1, I have considered here, after writing this factorial 3, psi alpha 1 is this one, then these 4, this term, this and this one. I have left this row and this column. Rest of the 4 term basically I have used. So psi alpha 1 is the first one with positive sign, this is with negative sign, this is with positive sign, and then after the expansion of it. So psi alpha 1 is this one, psi beta 2, psi gamma 3, right? This is psi beta 2, psi gamma 3, and with negative sign for the next two terms, minus psi alpha 1 as it is, and this psi beta 3 and psi gamma 2, this one. So this is the expansion of first term. Now for the second term is with negative sign, so I have mentioned here negative sign. Psi alpha 2 expansion with respect to this term, so leave this row in which that term lies and column. So now I have this one, this term, this and this one and this. First of all, this psi beta 1 psi gamma 3, psi beta 1 psi gamma 3 with psi alpha 2, and then after psi beta 3 and this psi gamma 1, psi beta 3, psi gamma 1. By this way I am writing all these 4 terms. And now for the third one, expansion with respect to this, that is which with plus sign, plus psi alpha 3, and expansion with these 4 terms. So now psi beta 1 psi gamma 2 minus psi beta 2 psi gamma 1, this one. So by this way you can see here 1 2 3 4 5 6 total 6 term. So this is the normalized antisymmetric eigenfunction. If one have to write for any number of particles the antisymmetric eigenfunction, then one have to use this selector determinant in this form. So now I have to check that this antisymmetric eigenfunction is valid according to the Pauli exclusion principle for 3 particles or not. So each term of this linear combination is a solution for the same total energy to the time independent Schrodinger equation. And now if suppose alpha is equal to beta, then when I am writing alpha is equal to beta, my means here to use it that 2 particles are in same quantum states. And again I am repeating, when I am using quantum state, it means that space and spin quantum state mean. Alpha is equal to beta for 2 particles because Pauli exclusion principle says that 2 particles cannot be in a same quantum state. So alpha and beta are quantum states and 2 particle. So if psi a is equal to 0, it means 2 particles are into the same quantum state. It means that. So let us see. When I write alpha is equal to beta, here alpha and this is beta, and there are 2 particles 1 and 2. If I write alpha is equal to beta, that means this is also alpha. Here beta is equal to alpha. This is beta, this is alpha, this is beta, alpha. Here beta is equal to alpha and this beta is alpha. So for the first term, psi alpha 1, psi alpha 2, psi gamma 3. If you see this term in rest of the terms, you will find that here this is psi alpha 2, psi alpha 1, psi gamma 3. It means this term and this term cancel out. Now for the next one, psi alpha 1, psi alpha 3 and psi gamma 2. Psi alpha 1, psi alpha 1, psi alpha 3, this term, and psi gamma 2, psi gamma 2. So this is with negative sign and this one positive sign, cancel out. And similarly, if you can see here that for these 2 terms, psi alpha 3, psi alpha 2, psi alpha 3, psi alpha 2, and this psi gamma 1 cancel out. So as a result you will get 0, which satisfy the Pauli exclusion principle. So by using the selector determinant, one can write the antisymmetric eigenfunction, which is the condition for the Pauli exclusion principle, right? And one of the important point that Pauli exclusion principle specify the properties of only electrons, not of the atom. So thanks for watching this video. If you have any question or any doubt, you can write the message just below into the box. Thanks for your. If this video is helpful, then please like and subscribe the channel. Myself, Dr. Sushil Kumar, and if you want to see such more videos, you can visit my blog www.apniphysics.com.